Hello everyone, I am Sahil Sawant and I am currently pursuing my MTech in Computer Engineering at VJTI Mumbai with a background in Electronics and Telecommunication and research experience in RF systems and radio astronomy. In the first episode, we understood that a signal is a variation that carries a certain amount of information. In the second episode, we saw that signals can be viewed in frequency domain using Fourier. In the next episode, third episode, we discussed that sampling must follow Nyquist or we get something that is called aliasing. Today, we are going to go a little bit deeper because even if you follow Nyquist, engineering errors can still happen. Today, let's focus upon aliasing in practice and something equally dangerous, that is the spectral leakage. Let's quickly remind ourselves. Aliasing occurs when sampling frequency is lesser than twice of highest frequency component. When that happens, high frequency components fold into lower frequencies. The system does not crash. The signal does not disappear. It is lying to us. You think you detected a 10 Hz signal. In reality, it was 90 Hz but sampled poorly. Aliasing is the misinformation that is being provided by the signal. It is not the loss of signal. Let's look at real world scenarios now. Let us consider biomedical devices, that is the ECG device. If ECG sampling is insufficient, high frequency noise may appear as artificial low frequency components. And thus the diagnostic can be affected. In communication systems, that is the RF receivers, radio frequency receivers, improper front-end filtering can cause adjacent channel interference to alias into baseband. Thus, the result is going to be a fake demodulated signal. Now, let us look at an astronomical perspective as well. When we are observing a cosmic signal, improper digitization can cause RFI, that is the radio frequency interference, to fold into observation bands. We may interpret interference as astronomical phenomenon or astrophysical phenomenon. In scientific system, alias can create fake discoveries as well. This is why engineers don't just rely on EDC. Before sampling, we apply what is called an anti-aliasing filter. What does it do? It removes frequencies above Nyquist limit before sampling. But here is the catch. Real filters are not always ideal. They don't drop instantly to zero. They have transition bands. So, in real engineering, we sample these higher than theoretical minimum. This gives us a boundary. Engineering adds safety margin. Even if you sample perfectly, you can still make another mistake. These mistakes happen during the sampling process. But during analysis, it is called a spectral leakage. And it happens because in real life, we never observe infinite signals. We observe finite time windows. Fourier transform always assumes that a signal is periodic and extends up to infinity. But in reality, what we capture is a 1 second of audio or 0.5 seconds of ECG or few milliseconds of RF bursts. You cut a portion of signal. Now mathematically, that is always equivalent to multiplying our signal by a rectangular window. And multiplication in time domain is convolution in frequency domain. This spreads energy across all the frequencies. This spreading is known as spectral leakage. Now imagine you have a pure 50 Hz sine wave. Ideally, FFT should show one sharp spike at 50 Hz. But if your observation window does not capture an exact integer number of cycles, this FFT shows energy spread across neighboring frequencies. Instead of one spike, you get a smeared distribution. The signal appears less pure than it actually is. Instead of one spike, you get a smeared distribution. The signal appears less pure than it actually is. But why does it matter? Because a signal leakage can mask a weak signal as a near strong one, distort in frequency domain, reduce measurement precision. In RF systems, leakage may cause incorrect bandwidth estimation. In vibration analysis, leakage may hide fault frequencies as well. In astronomy, leakage can smear spectral lines. Again, not academic, but very real. Engineers don't just accept leakage, they reduce it using window functions. Instead of cutting signals abruptly, we taper it smoothly. Common windows are Hamming window, Hanning window, and Blackman window. These windows reduce discontinuities at boundaries, which reduces spectral spreading. But there's a trade-off between them as well. Reduced leakage versus reduced frequency resolution. Engineering is always about these trade-offs. Let's summarize what the differences are. Aliasing happens during sampling. It is caused by insufficient sampling rates. It results in frequency folding. Now, let us look at spectral leakage as well. Now, spectral leakage happens during analysis process. It is caused by the finite observation window. It results in frequency spreading, and aliasing is a sampling problem. Leakage is a windowing problem. Both are going to distort the frequency interpretations. If you remember one thing from today, that is, signals are not lying. Poor engineering interpretation does. Aliasing and leakage are not the signal problems. They are system design problems. In the next episode, we move into something equally important, that is the noise. Because in the real world, signals are rarely clean. And signal processing is largely the art of separating signal from noise. Welcome back to Signals and Stars.